Hello, and welcome to our pre-lab activity associated with the bone lectures and lab. Now, what we're going to do here is, again, reinforce the concepts that we started out with within the lecture, as well as provide you with additional information for being able to go through and identify the images as you're going through the slides and the images in the laboratory activities. Now, the first thing to keep in mind is that bone is going to be an example of a specialized connective tissue, skeletal connective tissue. So it has the same characteristics of generic connective tissues with some added modifications. And so one of the most important things to keep in mind is that when we look at the bone matrix, we're going to have both organic components. Now, the organic components are the osteoid, about 50% of the bone volume, 25% of the bone weight. Predominantly type 1 collagen for the strength that it provides. Again, very strong, very resistant to stretching. Small amounts of ground substance like proteins, carbohydrates, proteoglycans, and lipids. But in essence, we're going to establish this type 1 collagen matrix, the organic components of bone, the osteoid, and on top of that, we're going to add in these inorganic components. And it's going to be these inorganic components that are the predominant tissue component. About 50% of the bone volume, but about 75% of the bone weight. And it's going to be these inorganic components that give the bone matrix its hardness, making it kind of the hard, strong structure that it is. And now the inorganic components are going to be the calcium and phosphate ions that come together to form the hydroxyapatite crystals, which essentially crystallize on that type 1 collagen matrix that's been established and solidify it, make it much harder, much stronger than what it would be just as type 1 collagen as a more generic connective tissue. Now, the strength associated with this as a specialized connective tissue also presents some challenges when we want to study it. And so there are two ways in which we can study the bone. The first, over here on the left-hand side, is to take a look at ground bone. And what we've got here is essentially a section of bone where we take it, we put it up against a grinding wheel, and we grind it down until it's very, very thin. We're going to use something like India ink here that's going to fill in the spaces, and we can see, like kind of those central locations. You can see the lacunae where the cells are going to be located. We can see the filopodia kind of extending through here. But we're going to see, in essence, a remnant of what was there because we've artificially ground this down into something thin enough that we can shine light through. In contrast, over here, this looks more like a biological slide that we've looked at already within the course. We can see, nuclei. We can see the pinkish staining proteins of the collagen in there. We can see something in hemotoxin and eosine stained specimens similar to what we've seen before. And this is an example of demineralized bone. Basically, what we did is we took a section of bone and we put it in acids, and the acids leached out. They drew out all of the calcium and phosphate. They drew out the inorganic component of bone. So what is left behind are going to be the organic components. And so once we get rid of the hydroxyapatite, we get rid of the calcium and the phosphate, what's left behind can be processed as a dense connective tissue. And so that's how it looks more as a more normal histological image, similar to what we've seen previously within the course. So we've got two ways in which we can study the bone. The next thing we're going to look at are going to be the cells of the bone. Osteocyte, os for bone, cyte for cells. We're going to be looking at the terminally differentiated bone cells. They're going to be trapped within the matrix. And so we can see the lacunae where these cells are going to be sitting. So in this, again, a ground specimen of bone. So we can't see the cells themselves, but we can see the spaces that are left behind. So we got the lacunae that they're sitting in a pen. We can see the canaliculi, these thin kind of canals that are going to extend from one lacuna to the next, down to another lacuna, down to another lacuna, ultimately getting to the Haversian canal at the center. But keep in mind that in a living specimen, we would have an osteocyte sitting within the lacuna. A cytoplasmic process is called a filopodia, extending through this and connecting up with that next osteocyte. Ultimately, the materials that are being transported within the Haversian system at the center here are going to be passed through these cells to these osteocytes that are trapped within the bone matrix. Again, because of the hardness, we can't have diffusion occurring through the bone. The other type of cells we can see are going to be the osteoclasts. The osteoclasts are going to be the bone resorption cells sitting within a shallow depression or Howship's lacuna within the bone. Relatively large cells, multinucleated cells, multiple nuclei, often 2 to 50 nuclei. Acidophilic cytoplasm because a lot of acids a lot of lysosomes, a lot of mitochondria, a lot of Golgi. And these guys, these osteoclasts, are going to break down the bone. And they're going to do that by releasing acids to leach out or essentially dissolve the calcium and the phosphate, as well as enzymes like collagenases to break down the collagen matrix. If we take a look at the surfaces of the bone, we've got a periosteum around the outside, peri for around, os for bone, so the structure around the bone. Again, we're going to be looking at this at all regions outside of the bone except for the articular surfaces, except for the locations where we're going to have cartilage at the joint cavities. Again, similar to what we saw with cartilage, we're going to have an outer fibrous layer and two in this region here as a dense connective tissue to anchor the bone into the surrounding tissues. Along the inner region, we're going to have that osteogenic, os for bone, genic for birth, osteogenic, where we're going to have that bone precursor cells that can be differentiated and start to produce bone along the surface here. We can have Sharpie's fibers, and we look at this at higher magnification, which are essentially perpendicular collagen fibers, which are going to be anchoring the periosteum into the bone itself. So a Sharpie's fiber would be running kind of in the orientation I'm indicating here with the arrow. We take a look at the endosteum, the inner surface of the bone. What we're going to have is a thinner, condensed reticular connective tissue, so that kind of jungle gym type structure, forming a scaffold that allows cells to migrate through the region. Now, if we've got red bone marrow, what we're going to have is hematopoietic cells, so lots of nucleated cells. If we have yellow bone marrow, what we're going to have are mainly fat cells, so mainly white adipocytes within the bone marrow cavity. If we take a look at the organization of the bone, again, spongy bone, we've got that cancellous appearance, and so we're going to look at a 3D lattice, kind of a 3D matrix. It's going to be characterized by kind of the pink staining, lots of collagen that we can see through here, high magnification, be able to see the osteocytes, but that very pink staining appearance of the bone, lots of open spaces between them, and so we can find this in like the marrow cavities. These are going to be composed of either primary or secondary bone. So it can be looked at as either woven or structures that have distinct haversian canals and haversian systems. Spongy bone is going to be found at the epiphysis, the bulbous ends of the mature long bones, as well as the core of the short bones and between the thick plates or tables of the flat skull bones. Compact bone or dense bone or cortical bone essentially has that pink staining appearance that we would characterize with the bone because of all that type 1 collagen that packed there. See some osteocytes trapped within the bone matrix, but it's lacking the large spaces in the trabeculi. And so we're looking at it, and it's dense because it's essentially bone all the way through the region. It's going to be composed of secondary bone. We'll talk about what that means on the next series of slides. But we're going to find this in the thick diaphyseal cylinder of long bones, the thin covering over the epiphysis, as well as the tables of the flat skull bones. If we take a look at how bone grows, we've got the endochondrial ossification. So again, keep in mind that what we're looking at is the cartilage at the epiphyseal growth plate. And so over here, someplace kind of in the lettering that we've got over here, we'd have that articular surface. We'd have the joint cavity occurring over here. So we're going to have hyaline cartilage here. Again, cartilage cells, the kind of grayish staining appearance because of the hyaline cartilage. But we want to maintain that. And so what we're going to have is kind of normal cartilage over here, and then we're going to have a zone of proliferation. In the zone of proliferation, the cells are going to line up. We're going to have lots of mitosis going on, very strong proteoglycan matrix. So we're going to see kind of a more basophilic staining appearance kind of through here. And these cells are going to be dividing, in essence, pushing off that reserve cartilage, pushing off that articular cartilage, so that the process of bone formation coming over here from the right doesn't overtake it. We take a look at that. Again, we got the zone of proliferation over here. In the zone of maturation, what's going to happen is the cells to start to increase in size, and we'll see that in the zone of hypertrophy and calcification in here. So in essence, the chondrocytes are going to expand, they're going to get larger, they're going to push against the matrix, and when these cells die, you don't want the matrix to collapse back down, to kind of fill back in the spaces. And so what's going to happen is the cartilage matrix is going to become calcified. And so what we're going to have is going to be a calcified cartilage matrix, still kind of that bluish or kind of gray staining appearance that we saw previously. But we know that it's going to have calcium there so that when the cartilage cells, the chondrocytes die, they're not going to be essentially allowing that space to come back in. So then we're going to have blood vessels coming in, and we're going to have a zone of cartilage degeneration. And so the lacunae of the cartilage is going to break down. It's going to be invaded by capillaries. Again, capillaries are going to be important because when we start laying down bone, we need the capillaries there because we're not going to have the ability to have diffusion like we would have within a region of cartilage. And so we're going to have osteogenic cells coming in, and they're in essence going to lay down bone on top of this cartilage matrix. And so you have the grayish staining appearance, but then ultimately you're going to have the pinkish appearance of bone being deposited on top of that calcified matrix. Later on, we're going to have osteoclasts and another round of osteoblasts come through and kind of clean up this region and allow us to form true 100% bone on bone, as opposed to what we've got here with this hybrid where we've got bone on top of cartilage. And this is going to finish up our overview of the bone tissues. If you have any questions, feel free to email me at hoffmanj@arcadia.edu. Thank you.